Hello, welcome back. So let's look at the big picture. Remember that not meeting the assumption of independence is bad. And when we don't meet the assumption of independence, everything gets screwed up. So we need to take a mixed models approach, which means we fit separate regression lines to each of the clusters and then basically average those lines. And the average of those lines we call the fixed effects. And the individual lines we call the random effects. And we also talked about visualizing and how you can really only visualize a few clusters at a time to see if the model fits the data. But if you look back at our previous discussions on regular linear models, you know that we have more than just visuals to assess models. We also have estimates. Or really the question that we need to be asking is, how do we evaluate models? And as I'm thinking about it, this probably ought to be its own video. I think I'm the only one who thinks about it this way, which means I'm either a genius or something else. Anyway, the way that I think about it is there's three ways to evaluate a model. One is visually, and we can use visuals to see how well the data fit the model, or how well the model fits the data. And we also have estimates like slopes and intercepts and Cohen's d and correlation coefficients and that sort of thing. And we also have model comparison estimates. And with the model comparisons, that's where you get like the AIC and the BIC and the base factor and the p-values, and I guess you could consider R squared as kind of a model comparison metric, or you can consider an estimate. Anyway, that's how I tend to categorize different information. For mixed models, we already talked about how to visually evaluate them, but how do we go about computing estimates? That is a good question. First, let us define estimates. Estimates are concrete numbers that give precise information about a single model. That's pretty tweet-worthy, I would say. Again, concrete numbers that give precise information about a model, a single model. Let's look at some examples. So like a slope, it is a number that tells you how much y increases every time x increases by 1. So again, it's a concrete number that gives you precise information about a single model. Or Cohen's d. It is a number that tells you how many standard deviations different two groups are. Or a correlation coefficient. So it is a number that tells you how correlated two variables are. So all these are estimates, and these estimates give us very precise information about a model. Let's look at an example in mixed models. So in this model, we're going to use LME4 as we always do, and we're going to fit a model where we have alk use, which is alcohol use, and I think that's number of drinks per week. And we're predicting alcohol use based on peer alcohol use, and I believe, if I remember right, that this is the number of weeks their best friend drinks per week. And then age 14, that is the number of years since they were 14 years old, and so if they are 14 in the sample, their number is 0, if they're 15, they're 1, etc. And then we're specifying that age at 14 is a random effect, and then we are saying that these vary by ID, or each individual has their own unique slope. And if we were to use the estimates function in FlexPlot, it's the same! Wow! When we used linear models, we did estimates model, or whatever our model's name was, and it gave us estimates. And now, when we're using mixed models, it's the same. Wow, how convenient. Whoever made FlexPlot is a freaking genius. Yeah, thank you! And if we were to do that, we'd get fixed effects, random effects, and the ICC and design effect. And we'll go ahead and walk through each of these one by one. So fixed effects, we got an intercept of negative 0.03, a peer slope of 0.67, and an age at 14 slope of 0.27. So these are interpreted exactly the same as you would with a regular regression, except that it's the average effect. The intercept means they drink negative 0.03 drinks per week when they're 14 years old, which remember with age of 14, the value of 0 means they are 14. Because remember, an intercept refers to the predicted value of y when x is equal to 0, so x age 14 equals 0 means they're 14 years old. And when they have 0 peers to drink. So basically, if they don't have any peers who drink and they're 14 years old, we predict that they will basically drink 0 drinks. And that makes sense. Faith in humanity restored that we don't have 14-year-olds getting drunk off their asses. The peer effect. Every peer they have who drinks, we expect them to drink 0.67 more drinks per week. I think that's how it is. Actually, it could be for every can of beer, however it's measured, their peer drinks, their best friend drinks, we expect them to drink 0.67 more drinks per week. And then we got age 14, so every year past 14, we expect them to increase drinking by 0.27 drinks per week. So when you go from 14 to 15, we expect that number to increase by 0.27. So that was pretty easy. Again, it's interpreted almost exactly the same with regular regression, except now we got to consider it as the average of the random effects, but basically it's the same. Now we shall look at the random effects. Remember, not every cluster, in this case person, will have the same intercept. I don't know why I slipped into an accent there, but that's okay. They shall vary. In other words, each individual's intercept is going to vary, which makes sense. So std.dev tells you how much they vary. And so for the intercept, it says 0.58274. So it's saying, on average, the intercept deviates by 0.6. Now, that's probably hard to kind of conceptualize what's going on, but let me go ahead and show you a plot. So this right here is a plot of the model that we have. So the solid black line is the fixed effect, or the average effect. And we see that along the value of age 14 of 0, we see lots of different lines. And so each of these lines has their own unique intercept. And if we were to average the deviation from the fixed effect, we would find that the average deviation is 0.58. Or in other words, that's how much they vary in their intercept up and down. Now, what about the slopes? Excellent question. Each slope has its own slope that deviates from the fixed effect. So how much do they deviate on average? Of course. So when we look at the data, we see that it is 0.39389. What does that tell us? That tells us on average, the slopes vary by about 0.4. So we'll go back again to this visual. This is a little bit harder to conceptualize, but basically notice that each of these lines has a different slope. So like this one is a pretty steep slope, this one is a pretty shallow slope, and the average deviation is about 0.43. So to put that more concretely, let's say that, well, actually, let's look at the actual slope. So the actual age 14 slope is 0.27, so we would expect the majority of slopes to fall between 0.27 plus 0.4. So let's just round it off to 0.3 and 0.4. We expect most slopes to range from about 0.7 to negative 0.1. That's basically what that's saying. And then we have residual variance. So these are interpreted almost exactly as they are in regression. So each dot in the plot deviates from its cluster regression line. And I'm going to use a different example. I'm going to use the math data set because it has more individual data points. So if we look at this visual, we see that those red dots deviate from their red line. And the amount by which they deviate on average is approximately 6.0688. Now, of course, I'm loosely interpreting this because this is just for one school, but it's averaged across all the schools. And the last thing we see is the core, which is negative 0.075. I'm not going to explain what that is, just because I've never found it useful to actually understand what that is. If you are an expert in mixed models and you think I am a complete idiot and totally wrong, please let me know, but I've never found it useful to interpret. I know what it means, but I don't know why that's particularly helpful. That's all I gotta say about that. So that basically sums up the fixed effects and the random effects. In the next video, I'm gonna teach you about the other part of it, which involves a little bit of background, so that's why we're waiting until the next video. But first, let's review our learning objectives. Number 1, 3 ways we evaluate a model. Again, we use the visuals, and we use estimates, and we use model comparisons. In this video, we basically covered the majority of the estimates. Or how to interpret fixed effects. Again, we interpret those just as we would with regression. How do we interpret random effects? Basically, what we're looking at is we're looking at the variance of the slopes or the intercepts, as we did in this video. How do you interpret residuals in a mixed model? You interpret in a similar way that you would with regression, except now you're looking at the deviation of each individual dot from their respective random effects cluster, rather than from the one and only regression line as it would be in traditional regression. And hey, got a question for you. Have you taken a class at simplistics.net yet? Net yet? Net yet? I sure hope you have. If you haven't, what are you doing? Come join us. You will have access to a Canvas course where I will guide you through the topic of mixed models, complete with discussion boards and quizzes and exams and all that fun stuff. So I hope to see you over there. And also, if you're watching this video before August 2024, you can do a live class where you get live interaction with me via Zoom. So I hope to see you there. And yeah, I'll see you in the next video where we're going to talk about variance explained and stuff. Peace out.